Hi there. In our last video, we talked about how to augment our data and save those images, given that you have a small sample size. This is really useful for things like image classification. And now we're going to talk about how to do this at runtime of a ConvNet, a convolutional neural network. So let's go right into it. So first thing we're going to do is do our imports. So from keras.models, we're going to want to import sequential. From keras.layers, we're going to want to import conv2d and max pulling 2d. And now from, let's just make it a little nicer because we have quite a bit here. We're going to want to also import activation, dropout, flatten, and dense. Typical things that you need in a neural network. And then from keras.preprocessing.image, things that you might remember from our last video, you're going to want to import the image data generator, array to image, image to array, and load image. Things we might need as well. Let's just throw it in here. Pandas as PD. Ooh. We might need P. Okay. So first thing we're going to want to do is go ahead and make our data gen. So our data gen is equal to this that we used last time. So in case you didn't watch the last video, we have all these different arguments which allow our image to be transformed in different ways, like rotating, shifting it in the X and Y direction, shearing it or cutting the image, zooming in on the image, allowing the image to be flipped, how we fill the image, which is those lines that you saw, as well as the brightness range. And now we want to go ahead and define some characteristics for our neural network. So we're going to want to define our kernel size, if I can spell kernel size, and we'll do this as a 3x3. And we want our pool size, that's going to be a 2x2. Our first filters, set at 32. Our second filters, or the number of nodes in each layer, depending on how you look at it. Third filters, that's of course 128. And now we want our dropout for our convolutional part. We'll do 0.3. And then for our dropout on our dense, we'll just roll with 0.3 as well. 0.3 is pretty safe. We don't want to do too great of a dropout. This is just to make sure we aren't overtraining. Something important though that you may run into, given that our images are different sizes, we want to make sure that all of our images are the same size. So kind of like a regularization. So we'll just say image size is equal to 150. Yeah. So let's go ahead and set up our model now. So let's just do model setup. Yep. And you know what's about to happen if you've done this before. That's just where we do all of our model.adds is equal to sequential. So now we want model.add. That's a conv2d with our first filters, our kernel size, and activation is equal to ReLU, rectified linear. And then let's do our input shape. Our input shape is equal to image size, and 3. So this 3 would be a 1 if the images are gray. So if you use grayscale, anything like that, if you use OpenCV before all of this, that's just another way that you could transform your entire directory into grayscaled images. And if this model is going to be run on the desktop, it's probably best to do grayscale, honestly. Now, if this is running on a mobile device or something like that, well, you could probably do grayscale anyways. But for this situation, we'll keep it colored. Colored is definitely more difficult, more computationally intensive, because again, you're working with 3 values per pixel instead of 1 value per pixel. So let's keep adding here. Model.add. We'll do another comp2D. First filters, kernel size, and then we'll do activation is equal to ReLU again. We'll do that one more time here. And now we will do a max pooling here. Model.add max pooling 2D. And pool size is equal to pool size. That's why you define these variables earlier, because you don't want to make mistakes when you're doing this. And it's just so much more readable. So much more readable. So now we want to go ahead and do our second filter set. So simply call second filter. Again, this is all ReLU. Okay, let's do 3. And now we're going to want to do a max pool and a dropout. Oh, we need to add a dropout here, actually. A dropout of dropout conv. Okay, and we'll do the same thing after the max pool. Very important. And then we will do the same thing for the third filters here. Okay, so that's good. So after we've done the 2D ConvNet, we need to go ahead and flatten this for our dense layers. So now we are going to, break down the size of our net into something that we can actually read eventually. And then we want to go ahead and add another dropout after this 256 node. That's a dense. So this one depends on your class size. So model.add. Let's go ahead and add a variable here. Classes. So in our case, it's 3. In your case, it could be 30,000. Could be 300,000. Totally depends on your data set, what you have. Know your data set. Very simple to count the number of classes you have. Our case is only 3. You gotta drop the number of nodes you have to your output. So the last layer should always be the number of classes that you have. All right. So now we want to compile our model. In our case, we'll do model.compile. We'll do an atom call. I think we imported atom actually. Yeah, I don't think I imported atom. Let's go ahead and import atom. So from keras.optimizers, import atom. And we need a few more actually. From keras.metrics, import categorical cross entropy. Let's see what else. What do we need? We need our callbacks. From keras.callbacks. Let's import quite a bit here. Will we use early stopping? We might. We'll do reduce loading rate on plateau, which is a really great thing that I don't know a lot of people know. And we'll use TensorBoard. So we'll import all these. Come back down here. So now that we have atom, we will go ahead and specify our learning rate of, let's do probably unnecessarily small for this data sample, but that's okay. And for loss, we'll do categorical cross entropy. Just copy and paste that. You don't want to watch me spell that. And then for our metrics, we will do accuracy. Okay. Okay, now we will grab the summary here because it's so nice to see what's going on. All right, now we need to do our data gen. So what we need to do is let's specify our batch size. Batch size, we'll say 16. And we will do our train data gen is equal to image data generator. So we'll do rescale 1.0, 255. You might recognize that if you've normalized images that are colored. That's quite an important attribute to do. Zoom range, we'll do, and horizontal flip is true. Okay, so now we'll do test data gen is equal to image data generator, and we'll rescale that 1.0 divided by 255. Okay, now we will do our train generator from flow directory. So we'll just say train data generator actually, right? Actually, no, let's do train generator. Yeah, we'll do train generator. Yeah, naming variables is very hard. And we'll say train data gen dot flow from directory. And now we will specify our directory. We'll just say images. And let's get some more specifics in here. So target size, for example, we want our target size to be what we specified earlier, image size, which is 150 by 150. And we want our batch size to be equal to batch size, which is just 16. And we want our class mode, class mode equal to categorical. Okay. That all looks good. And now we will go ahead and say our file path is just equal to, let's just do tutorial.h5. And let's set up our checkpoint. So our checkpoint is equal to model checkpoint, file path. We want to monitor our val accuracy. And our factor, this is how much, let's do verbose equal to 1, save best only is equal to true, and mode is equal to max. Okay, so this is our model checkpoint, which will only save the best model, so it'll check every previous model with its current accuracy. If the val accuracy, which is the validation accuracy, has improved, it will overwrite the old model with the new model with the better val accuracy. Very, very nice. A lot of people that I've ran into do not know that for some reason. Checkpoints are so important. We also want to to reduce our learning rate. So reducing learning rate on plateau. Let's say you're training your model and it's no longer getting more accurate. You've been through 50 epochs. The accuracy is not improving. Do you want to stop the training, reduce the value, have to rerun the whole thing? No, you would really like the learning rate to be able to change on the fly, right? And that's exactly what this does. It's amazing. So again, we're going to do validation accuracy. And we want to have a factor. This is how much we're willing to let the learning rate reduce. So we'll do 0.5. That's okay. Patience. This is how many epochs we wait until we reduce the learning rate. In this case, we'll put 2. We'll do 3. And then verbose is equal to 1. And mode, we want that to be a max. And the minimum learning rate, we'll do what we specified up here. Well, no, we'll do a little less. Yeah, we'll do this. And that looks good. Okay. So, we don't really need TensorBoard, but I'm gonna go ahead and do it because it's kind of an important thing to know how to do. So let's say TensorBoard logs dir is equal to logs. All right, so now you want your callbacks. Is this equal to all these things that we just specified? So we have checkpoint, reduce learning rate, and TensorBoard callback. All right, so now finally we want to go ahead and fit our model. So we'll just say fitting is equal to model.fit. So we want our train generator. Always trying to get me there. Train generator. Steps per epoch. In this case, we'll do 2,000. We'll do 200 divided by batch size. And then we'll do validation data is equal to validation generator. Did I not make the validation generator? Oh, I skipped that. Okay, so we also need to do a validation generator, which is pretty similar to this. Batch size, kind of global. Yep. So everything else is going to be the same here, just a name. Now, ideally, yes, you want different directories for these. You would like images, train, images, validation, images, test. But in our case, again, we're working with a very small sample size. That's the whole idea. So validation generator, yeah, and then we'll do validation steps. We'll do 800 divided by batch size. And then we'll do epochs. Oh, let's do 30 in this case, just for the video. Verbose is equal to 1. And we'll say callbacks is equal to our callbacks. Okay, so that should be everything. Let's go ahead and give it a run. See if it gives us any complaining. I'm sure it will. It's quite a bit there. Oh, let's see. Sequential object has no attribute. Okay, distribution. Initial epoch. It looks like the issue was with callbacks. Interesting. So let's just go ahead and remove callbacks for a moment here. See if that fixes it. Okay, so there's the callbacks. That's fine. So it's training here. See the first epoch's accuracy, not quite so good, right? So if we take a look at our actual model, we can see the shape of the layers, the number of parameters per layer, and our total number of parameters. So we're looking at quite a massive number of params. 6 million, right? No, it's not that many. But you can see our accuracy is improving on our validation set. We have a validation accuracy initially of 0.33, and now we have one of 7. So it's getting greatly increased here. And you can see our normal accuracy here went from 0.36, 0.5, now we're rocking at 0.93. So it's getting better and better. As for our callbacks, I'm pretty sure the issue lied with, oh yeah, it lied with TensorBoard. So I didn't create the log directory, so I'm sure that's the issue. You can see our validation accuracy is already 100%. Our loss is decreasing very rapidly. Both our validation loss and our regular loss. So this model will actually probably go into overtraining, especially with an epoch of 30, which is why it's so important to have those callbacks. So let's go ahead and stop this. Let's rerun it without the TensorBoard callback in there. Let's see if that that runs. Yes, it does. So the TensorBoard callback was giving me a little bit of issue there, but not a big deal. You just have to create a new directory in here called logs, and that should fix it. And you can use the same code that I had previously. So that really sums up the video. Basically, you need to use the image data generator from the Keras preprocessing image library to do all of your image augmentation. Build up your ConvNet. Pretty typical ConvNet here. Quite a bit of layers. This will give you very accurate results. This is a great layout that you can use pretty much with any image classification. One thing though, ideally you do want to train and test and validation set. But given the scenario that I'm trying to produce here of a small image data set, that's okay. So this really sums up the video. If you have any questions about anything at all, please ask in the comments below. Thank you. Have a good day.